All right, so the first question for today, I'm going to give you a diagram to study briefly, and there'll be a statement under the diagram. Let's see how it goes. So, see this. Please, no side talking, so that there could be no noise. I don't think you used to watch the video because if you watch it, you will see the noise, lots of noise inside the video. So, this is the diagram, and I'm going to bring the statement on there. So for this given diagram, so we have this statement which says, so this is the statement under the diagram for Sarah. Then I'm going to bring the options. So, let's see. So these are the options for Sarah. So what do you think?
You know when I was sleeping? This is the opening.
Hello, are you
Oh, the
talking
diagram
or
above illustrates a beam of parallel rays. Sorry?
continue?
Sorry, I can't hear you very well.
Continue. Can you hear me now?
Yes, we can.
Okay, continue.
The diagram above illustrates a beam of parallel rays from a distant object O, incident on one side of the total reflecting prism, which diagram does not represent the correct part of the beam when it emerges from the prism.
Okay, so
Can you move in that? A W B X C Y D Z. Incident on one side of the total reflecting prism, which diagram does not represent the correct part. So W.
W. What?
W.
Okay, why do you think it's W?
Sorry, sir.
Yes, why do you think it's W?
Because from this angle, it's not curved.
Mm, um,
I cannot hear you, sir.
can you hear me now? Are you hearing
Yes,
me?
yeah, but your voice, your internet isn't.
Yes.
Okay, you can hear me.
I'm hearing you.
So, the incident ray goes in and it's reflected outward from the other to form an emergent ray. So, if you look at this, we look at all of the diagrams, starting from this first one, we have the incident ray, then it's being reflected back inside, then it goes out from the other way. So that W enters and comes out at the other way around. But if you look at X, it's coming out back from where it enters from. Are you getting what I'm saying? Can you hear me? Hello?
Yes, sir.
Okay. So this X is the
We
one
can
that
hear you,
does.
Yes.
sir.
Okay, yeah. So this X is the one that doesn't show the correct path. Z shows it, W shows it, and Y shows it, forming the emergent ray. That is the E, E, and E. But this is a part of the incident. The emergent does not come out from the incident as well. So the correct option is X, not W. Is that clear? Is that clear?
Yes, sir.
Okay. Though in past question they
Please
picked
wait.
in past question they picked W, but that is actually incorrect. Okay.
Yes, sir.
Okay. So the next question will be for Tai. Let's see.
Sir, please wait.
Let's go to
Sir.
Don't worry. I'm going to send the note over to you. Okay.
Sir.
Or you don't used to get the note.
I'm not going to be copying again when I still have so much to do.
There you can go.
Sir, wait.
Mm.
So I'm coming. I'm the first writer.
Yes, the second line. So,
So
the answer should be
the answer should be what? Yes, the answer should be what?
so. I'm not too sure.
And just try. Just try.
This is step up. So let me go for A.
Okay. Can you all see this?
Sir,
Can you all see this image?
it's very small.
But you can see what is there. Okay, wait. Let me make it a bit
Step
bigger.
up transformer.
Hold on.
Sir, step up transformer.
Hold on. Calm down. Calm down. Okay. Let me see if it can be. If the image can be a bit bigger, so that. Okay. Can you see the image now?
Yes, sir.
Yes, sir.
Now listen carefully. Listen carefully. What I have brought here is a step up transformer, but that's not the answer. Okay. Are you listening?
Yes, sir.
So just calm down. No talking, please. The one what I brought forth here is step up. Let us compare this. Smaller tons, okay, in the primary. Then more tons, okay. Are you hearing me? Are you hearing me?
Yes, sir. Yes, sir.
More tons in the secondary. That is for step up transformer. But in the primary of this, you have more tons, right? Right?
Yes, sir.
And smaller tons in the secondary. So what should be the answer?
B.
B. So please take note of that, okay? Is that clear?
Yes, sir.
So if it's going to be step up transformer, then the secondary turns should have more turns. I mean, the secondary, uh, the secondary side should have more turns. Okay, is that clear?
Yes, sir.
Okay, the next question will be for Mercy. Let's see what Mercy's got there. Okay, so hold on. So, what's your option for this one, Mercy?
Option and be the same to do.
What did you say?
Option B and C, they're the same thing.
Just pick your answer now.
They either the both of them. BC.
BC. The question is earpiece, right? What do you hear from
I
the What do you hear from the earpiece?
sound to electrical.
Wait,
Electrical to sound.
electrical to sound because it's from the electrical. Then you can hear sound, right?
Yes.
So take note of that. Okay. So the next question, as in when the speaker makes the sound, it goes into the phones and the components, that's electrical. Then it comes to sound to your ear through the earpiece. Okay, I'm going to bring the next question now. Hold on. So this is the question for Moses. Uh, Moses, try it. Read it. Let me hear. Yes, come.
Two identical cups.
Okay.
I should read on.
Yes, continue.
Two identical cups containing the same volume of water at 45 degrees Celsius and 5 degrees Celsius are left in a room at 25 degrees Celsius. Which of the following graphs correctly illustrate the variation of temperature
With time.
with time?
Okay. So check the graphs and see which option you think. Yeah. Which option do you go for?
I go for C.
Okay. Why do you,
Wait,
okay.
yes, C.
Why do you go for C?
Because the two waters are kept in a bowl, which are 45 and 5 degrees Celsius,
Okay.
respectively.
Okay.
And they are kept in a room temperature
Okay.
of 25 degrees Celsius.
Okay.
So they will have to, the rest. So they have
What is
to,
the rest?
Well,
There, there'll be heat transfer, right?
something like that, Sha.
There'll be
I
heat
don't know
transfer.
about.
What are the modes of heat transfer? What are the modes of heat transfer? Methods of heat transfer? Okay, Sarah, what are the methods of heat transfer?
the
Oh,
modes of
heat transfer, heat transfer. Mercy.
Actually,
What are the modes of heat transfer
modes of heat transfer.
or methods of heat transfer?
Oh, convention reducing and reduction.
And what?
Radiation, commercial radiation.
Radiation convection and
And what?
commission, no?
Convocation.
Convocation, yes.
And what?
Conduction.
Conduction.
Conduction. See, you guys cannot see.
So, why I'm mentioning this is because of the question that Moses answered. Moses, your option is correct, option C, okay?
Yes, sir.
And if we look at the graph, if you look at the graphs, the first graph is showing 45 reducing towards the room temperature but never crossing, 5 increasing towards the room temperature but never crossing, and nothing is, they are not even meeting the room temperature.
Sorry.
And the second one is showing a linear transformation of the two, meeting at the room temperature, and that one is also not correct. But the third one shows the equilibrium at a little bit higher than the room temperature, okay?
Yes, sir.
Which makes sense because the water at 45 will increase the room temperature slightly, and it will also affect the water at 5. The water at 5 initially, if the water at 45 is absent, are you listening?
Yes, sir.
The the equilibrium will not be up to 25. It will drop down the room temperature slightly. But because there is 45 there, so the 5 degree does not have that much impact. It's only being impacted upon, and that's why it's going higher. That doesn't mean it's going to get to 45, no. And that doesn't mean 45 is going to get to room temperature or even to zero, no. But they can agree at somewhere above the room temperature. Okay?
Yes, sir.
Yeah. So the next question is for
Sir.
Sarah. So hold on. All right. So this is the question. Let's look at it. You said you got 51.7, but let's look at it and see how it goes. So we can try to illustrate the question and say maybe this is a boundary. This is the boundary between the two. Uh, uh, yeah, and this is the, let me get the other side here. The normal. Okay. So probably this is a normal. And we have, what did you say? Okay. And we have the incident ray here. The incident ray.
Excuse me, sir.
Yes.
Don't worry, sir.
Okay. And the refracted ray. Say we have the refracted. This is the incident ray. So the refracted ray is going to be somewhere here, and
Okay.
it might be towards the normal or away from the normal, depending. So now this is the angle of incidence, angle of refraction. Then we have the angle of incidence to be 30. Then we are looking for angle of refraction. So we've been given the refractive index of glass So this is glass, and this is ethyl alcohol.
Ethyl alcohol.
So we now have the refractive index of this to be 1.36, and that of this is 1.5. So according to Snell's law, the we can say
It's
the
one was 1.36.
yeah. All right, just calm down, okay? So the refractive index of ethyl alcohol over the refractive index of glass will be sine I, which is in glass,
And I over sin R.
over sine R. Then we're looking for R, so sine R will be refractive index of glass, sine of incidence over refractive index of ethyl alcohol. So that means we have 1.5 times sine 30 over 1.36. So what is sine 30?
0.5.
So 0.5 times 1.5 is what?
0.75.
0.75 divided by 1.36. That will give you what?
Sorry? 0.75 divided by
0.5515. Okay. So we now have R that we're looking for to be arc sine 0.555. So what is arc sine 0.5515?
Mr. Send the question.
some about 33.46.
Yeah, 33.5, okay?
So it's B.
Is B, not
Yeah.
C. Is that clear?
Yes, sir.
Okay, so the next question will be for who?
Sorry.
Okay. So please listen. A 60-kilogram man stands on a weighing balance in an elevator. If the elevator accelerates upward at 5 meters per second squared, determine the reading of the scale. G equal to 10 meter per second squared. Okay. We know, you already know that F equal to MA, but this time around the A is going to include G. So because it accelerates upward, it will be A plus G because it's going to be heavier. Then we have F equal to mass times A plus G, and the mass is what? 60.
Mass is 60. Acceleration is 5 plus
10 plus
10.
5 meters per second
15
squared.
times 6.
That would be 60 times 15
15.
Newton. And that would be what?
900 Newton.
900 Newton. So let's take note of that. While the next question is for
Verse.
Mercy. Yeah. Next question is for Mercy. Good.
Yeah.
All right. Please listen.
So the answer
You said?
B. The answer B.
Hold on, hold on. I said listen carefully. We want to look at it together, okay? I just tick B because she chose B, okay? But I'm not saying it's correct or wrong, so let's look at it. You know the formula already, which is uh, linear expansivity is given by what? Change in length over original length times change in temperature. So that means if we bring change in temperature out, we're going to have change in length over original length times the linear expansivity. So with this, we have this is our change in length, change in theta, which is then theta, that's theta 2 minus theta 1 equals to this, then original
Change in length,
length times this.
original
So that
length.
means theta 2 will be what? Change in length over original length times what?
Times 1.2.
Then plus theta 1, right?
Yes.
So what is the change in length?
Um,
0.01%.
mm,
0.01%. So the length, the initial length was 100, right?
Yeah.
And 0.01% of 100 is what? Yes,
Hey, what's that calculator?
that is still 0.01, okay? That is 0.01 divided by 100 then times 100, okay? Is that clear?
Yes, sir.
Then original length is this. The linear expansivity is 1.2 times 10 raised power minus 5, then plus theta 2, which is what? 20. So if we are going to get this done, hold on, yeah, hold on, please. Let me see. So can you hear me now?
Yes, sir.
Okay, good. So I was attending to something shortly. Now, this is what we have, which is just mathematical expression. So what we have to do is we move this to the top. It becomes times 10 raised power 5. Oh no, we don't just move it like that. Let's do it separate. This is 20. I wanted to look for a shortcut before, but the main thing is that we are dividing. Let's multiply everything that's at the bottom because this is going to be 0. Let's say this is 0.01 over 100 times. If you change this to normal ordinary form, you have 0.000 um,
One, two.
0, 1,
One.
2, 1, 2, 3, 4, 5. So 1, 2, okay?
Yes, sir.
Then plus 20. So here now, we have 0.01 over, if you multiply this by 100, you have 1, 2. So that will be 0.0012 plus
20.
20. So try to divide this and tell me what you have. 0.01 divided by what? 0.0012. That
Eight
gives me
point.
8.3, okay?
Yes.
Plus 20. So this would be 28.3.
28.3.
So it's 28, not 38, okay? Is that clear?
Yes, sir.
So this is the correct option. Okay, let me see if we have. Okay, let's look at one more question before we round up. Okay, can you hear me? Can you hear me?
Yes.
Okay, okay, hold on. Okay, let me see. Um, so I have this question.
Yeah, you know, keep it same way.
Let's just look at this one together, okay? Who's supposed to answer this?
Moses.
Okay, Moses, just read it. Only read. Okay.
Alright. A moving coil galvanometer, which gives a full scale on deflection with 0.005 ammeter, is converted to voltmeter reading up to 5V using an external resistance of 975 ohms. What is the resistance of the meter?
Okay. Please let everyone listen carefully to this. Okay. Now, from V equal to high R, the I that we're looking for is the current of the galvanometer, which is 0.005. Then the R we're looking for, which is supposed to be V equal to, R equals to V over I, which is the I of the galvanometer. We have to take away the external resistance from it, which is that, let me just say small r. We take away the external resistance from it. So we now have, what is the voltage? Voltage is 5,
5.
okay? So we have 5 over 0.005, then minus 975. So what is 5 divided by 0.005? Yes,
1,000.
1000. So this is 1000 minus 975.
25.
That'll be 25.
250.
25 ohms. So
Ohms.
that becomes our option. So that is where we'll be running up for today. Um, okay.
Thank you, sir.
Thank you, sir.